Okay, so good morning, everyone. So I hope you got two main messages from my lectures yesterday. The first one was that with sufficient frustration, the ground states of classical frustrated magnets can be highly degenerate. And the second message was that although there's an extensive ground state entropy or an extensive number of ground state degrees of freedom, the ground states are not uncorrelated like a paramagnet. You still have a lot of structure in the set of ground states. And I illustrated these ideas particularly with the triangular lattice antiferromagnet, where I explained that you have power law correlations and you can understand these by mapping the ground state configurations onto a height model. And the advantage of doing that is that we can understand how to write a long wavelength description of the height model and actually do calculations with it and so on. And then the final point that I made in the second lecture yesterday was to do with excitations in the triangular lattice antiferromagnet. And that point is something which I'm going to take up in today's lecture. So I'd like to start by reminding and maybe amplifying what I was telling you about there. So these pictures are supposed to represent configurations of the triangular lattice Ising antiferromagnet with blue and red corresponding to the two orientations of a spin. And as you remember, the rule for being in a ground state was that every triangle should have two spins of one orientation and one of the other. And if I've drawn that correctly, then it's true of this upper picture. And I told you that we could map configurations onto heights using this rule for height differences as we move along the bonds of the lattice in the direction given by some orientation convention. And then the final point, which is the thing I want to emphasize to you now, if we have excitations in the system, which means that we have some triangles in the lattice with all three spins the same, then that introduces vortices in the height field, because as we go around the triangle following these rules, we have a height change of either plus or 6 units depending on the type of triangle. So we have an example of one of those excitations here. We've taken the picture at the top and picked this red spin and flipped its orientation so that it's a blue spin. And that process has actually introduced two excited triangles, the ones with these pluses in, because obviously both of them have all spins of the same color. And if the rule is that the height difference is generated by going in a particular sense around the up triangle, then you have a vortex of one sign on this up triangle and a vortex, on this up triangle, and a vortex of the other sign on the other triangle, because you follow the bonds in the opposite sense. So what I want to talk about now is what happens if we flip further spins starting from this configuration. Now, one possibility is that you introduce more excitations into the system when you do that, but we can choose instead to keep the energy of the configuration the same and simply move the excited triangles around. And these pictures show one way of doing that. So to get from the top picture to the bottom left, I flipped this red spin and made it blue, and now I can choose to flip this blue spin and make it red, and if I do that, I leave one of these excitations behind, and I move the other one triangle over, because here we have 3 blue spins in this up triangle, and then we have 3 red spins in the next up triangle over, and then I can repeat the process. So the point is, and it's the reason why this is worth emphasizing, we've got at the classical level an example of fractionalization of an excitation. So we flipped a single spin, and in an ordered magnet, that would have been a way to make a single excitation, a magnon or a spin wave. But now, in this system, we've been able to flip further spins without increasing the energy, simply separating the 2 excitations. So we set out to make one excitation, but actually we discover that we can only create them in pairs. Now, that was really just a recap of the end of my second lecture yesterday, but it's also a lead-in to the things that I want to talk about today. So today I want to talk about these materials that are known as spinices, and as I mentioned in the first lecture yesterday, they have magnetic moments on a lattice which is not 2-dimensional like this example, but rather 3-dimensional, built out of corner-sharing tetrahedra. But as you'll see, a lot of the ideas which we can develop in this 2-dimensional context also apply in the 3-dimensional context. So when I say a lot of ideas, I mean both a mapping to a long wavelength description, so there's some 3-dimensional analog of the height model that I introduced here, and in addition, this fractionalization of excitations. And this lecture will aim to cover both those aspects. Are there any questions here? Yeah.
Information about the vortex, can we get it from the eigenvectors of the exchange matrix?
No, I'm afraid the things that I told you about the eigenvectors of the exchange matrix are useful in a lot of situations, but not as a way of thinking about this triangular lattice Ising antiferromagnet. And the reason for that is basically that the degeneracy that you have here is specific to Ising spins. And if you, for instance, studied Heisenberg or XY spins on the triangular lattice, then you would find an ordered ground state in which the spins are at 120 degrees. And the self-consistent Gaussian approximation that I told you about is not really sensitive to the difference between Ising and XY or Heisenberg spins. So the self-consistent Gaussian approximation is actually a good way of thinking about some aspects of spinice, but it's a bit misleading if you apply it here.
So the height field is also multiple value defined this way.
When there are excitations, yes. That's the sense in which I mean it. It's the excitations are vortices in the height field.
Is there a deconfinement transition where you have these excitations that spread throughout the system? So you have 1 plus here and minus here. So is this, what is a deconfinement transition?
Yeah, well, I did mention briefly at the towards the end of the second lecture yesterday that you can establish the value of the stiffness of the height model, and actually these vortices are deconfined, so you're always in the disordered phase. And so the presence of vortices at finite temperature sets correlation length in the system. And as you go to low temperature, it's not that the vortices become confined, it's that their density goes to zero because of their core energy. Okay, so I want to talk about spin ice. So the materials, at least for the classic examples, are holmium titanate and dysprosium titanate. And the crucial thing is that the magnetism is all associated with these rare earth ions, and so we have rare earth ions, and they occupy the sites of a pyrochlore lattice, which is this lattice of corner-sharing tetrahedra, which I had a few slides back. So if we want to think about the magnetism, we first of all need to think about a single rare earth ion in this lattice, and to do that, you need to think about the effect of the electrostatic crystal field on the states of the rare earth ion. So you have holmium ions or dysprosium ions in the crystal field. And the low energy states are states with eigenvalues for J and M for the angular momentum of the ions, which are 8 and approximately plus or minus 8. I mean, the crystal field wave function has a superposition of different M values, but it's predominantly this. So you have two states for the magnetism which correspond to the magnetic moment pointing in one of the directions along an axis from the center of a tetrahedron out through the corner where the ion is located. So these are states pointing in or out of the tetrahedron. So the largest energy scale is a single ion anisotropy, which forces this moment to be aligned parallel or anti-parallel to these 1-1-1 directions in the crystal lattice. Because it's a large angular momentum, you have a magnetic moment which is unusually large. It's about 10 Bohr magnetons, which is quite important experimentally because it means that magnetic scattering is much easier to do. Magnetic neutron scattering is much easier to do from a system like this than if you're investigating something with spin-a-half moments. So this is all a single ion, but then we have interactions between the ions. So we have a coupling, and if you think about the interaction between two nearest neighbors, then one contribution is exchange. But because these are rather large moments, we also need to think about the dipolar interactions. And together, they give you a value for the Curie-Weiss constant, this quantity that we can extract from the temperature dependence of the susceptibility that gives us a measure of the strength of the interactions and also via its sign of whether they're ferromagnetic or antiferromagnetic. And we get something in the range of 1 or 2 Kelvin. So it's 1.9 Kelvin for the holmium compound or 0.5 Kelvin for the dysprosium compound. So in both cases it's positive, so it's ferromagnetic. And at first sight, that seems surprising because in the examples that I was talking about yesterday, we were really using antiferromagnetic interactions in order to get frustration. And the important point is that the frustration here comes from competition between the single ion physics, which constrains the orientation of the moments, and these interactions. And it happens that ferromagnetic interactions are what you need to produce the frustrated physics that I'm talking about. And I'll explain that by drawing a picture. So we have that as a picture of tetrahedron. Then the single ion anisotropy means that the moment at this site can either point into the tetrahedron or out. And then the ferromagnetic interactions mean that the moment, say on this site, would like to be as close to parallel as it can be to this moment without violating the constraint set by the single ion anisotropy. And the constraint means that it has to be along that axis, and clearly you do better with ferromagnetic interactions to have that pair of spins, one of them pointing in and the other pointing out of the tetrahedron. So in ground states, we have 2 in, 2 out rule, meaning that the spins are orientated in that kind of way. And that corresponds to the ground states of Ising antiferromagnet on a tetrahedron as well. And we simply have to say that 2 in, that the in spins correspond, say, to up, and the out spins correspond to down. Okay, any questions about any of that? It's 100 Kelvin or something like that, so it's absolutely the dominant scale.
Why not the transition metal ion?
I'm sorry?
Why not the transition metal ion? So the steel ice stable rather it's rarer type of ion. So my question is that can transition metal ion
Yeah, can transition metal ions produce the same physics? You wouldn't I think, be in this limit in a transition metal ion compound. That's to say, you wouldn't be so strongly dominated by the single ion anisotropy. So I mean, there are transition metal ion magnets where you have magnetic moments on the pyrochlor lattice, and for example, there's a series of chromite compounds where you have chromium 3+ ions, but in those materials the single ion anisotropy is very small, and so you represent them with a Heisenberg model. And some of the physics, which I'm going to talk about, goes through, but other aspects are different. I mean, they're very interesting in their own right, but they're in a slightly different category. Well, that was my point. Yeah. Okay, so as I mentioned, we have both exchange coupling and dipolar interactions, and these Curie-Weiss constants summarize the combined effect of both. And one feature that you realize of dipolar interactions is that they're long-ranged. Of course, they fall off like 1/r³. And that turns out to lead to some extremely interesting physics, which I'll discuss in the last part of this lecture. But for the first part, I just want to talk about a model of spinice in which we include only the nearest neighbor interactions, so that then we're really talking about the system described by an Ising model, whose entropy I estimated for you yesterday according to the Pauling formula, and we saw experimental evidence for the high entropy of the low temperature state. So at that stage, we're at about the same point as we were discussing the triangular lattice model, when I'd pointed out that you could have a high entropy because you could have spins with equal numbers of up and down neighbors, which were free to flip without any cost in energy. So just as with the triangular lattice antiferromagnet, the next stage was to produce some coarse-grained description in terms of a height model. So here we'd like to go to some coarse-grained description which will allow us to understand whatever the residual correlations are between spins in the ground state. And that's what I want to do in the next section of the lecture. Now, the first thing I want to say is that it's useful to have actually two lattices in mind when we discuss this problem. So one lattice is the pyrochlor lattice of corner-sharing tetrahedra, where the magnetic ions sit. So we can specify that as the magnetic lattice. And we can think of a second lattice by putting sites of this second lattice at the centers of the tetrahedra. And so that's a lattice of these clusters. And if you look at the pictures, you may be able to convince yourself that this second lattice is a diamond lattice. And again, if you think about it, you can see that the sites of the magnetic lattice correspond to the bonds of the cluster lattice in the sense that each site sits on the midpoint of a bond that runs from the center of one tetrahedron to the center of a neighboring tetrahedron. Okay, now when we talked about the mapping from the triangular lattice to the height model, one important but technical step was to introduce some orientations on the links. And what I want to do now is introduce some orientations in the same way in this three-dimensional problem. And the way we're going to do it is, first of all, to recognize that the diamond lattice is bipartite. We can separate the sites into two sets in such a way that a site from one set has, as its nearest neighbors, only sites from the other set. And if we call these two sets A and B, we can introduce an orientation so that the bonds of the diamond lattice are directed from A to B. So the idea is that the diamond is bipartite, and we can orient the bonds from sublattice A to sublattice B as a convention. And what we want to do is have some description of the ground states of spins on the pyroclore lattice, which, as I say, we can coarse grain. And the way that things are going to work out, we'll be able to represent the ground states in terms of a vector field, which takes the place of the height in the height model. And the statement will be that if the spins are in a ground state, then the vector field has zero divergence. So I'll introduce a unit vector on one of these bonds, and so that'll be a unit vector along the bond. And so this I labels both the bond and also the site of the magnetic lattice, because the two things correspond to each other. And I'll introduce a vector field which is in 3 dimensions, and the reason it's in 3 dimensions is because the lattice is 3-dimensional. So this vector field lives on the sites of the magnetic lattice corresponding to these bonds, and it's either parallel or anti-parallel to these unit vectors according to whether the Ising spin, which represented whether the moments pointing in or out of the tetrahedron is plus or minus 1. So if I go back to a picture of a tetrahedron, what I'm saying is that I associate these spins with flux of this field B, and I'm saying that there's some flux going into the tetrahedron when this spin is pointing in, and going out of the tetrahedron when the spin is pointing out. And the rule that in ground states 2 spins are pointing in and 2 are pointing out, that rule is the same as the rule that this flux has 0 divergence. The flux lines never end. So I'd really like to get this idea of the construction across. Is that clear to everyone? Okay, so you could, yes? So you can ask about the curl of B. Yes, and that'll be non-zero in general. So the constraint that the system is in a ground state is simply that the divergence is 0, and that's analogous to the statement for the triangular lattice case that the height field was single valued. And actually, I'll explain a link between the 2-dimensional and 3-dimensional problems in a moment. Okay, so at this stage, we haven't necessarily got anywhere. We've got an alternative characterization of the ground state, but if we stay with everything on the microscopic level, then we haven't got any simplifications. So the final step is to write down an effective theory which does some coarse graining for us. And to see what that should look like, we should look at a couple of pictures of configurations. And I'm certainly not going to try and draw 3-dimensional lattices on the board, but I do want to draw some pictures. So I'll draw them in a 2-dimensional version. So I want to take the 4 sides of a tetrahedron and draw them in projection like that, and to indicate the fact that there are interactions between all 4 spins, I'll draw across the center of the square, but you should be clear that there's not supposed to be any extra site here. There are just 4 sites at the corners. So then I can draw some configurations. And for instance, I could take something with spins like this, and okay, so unless I made a mistake, there should be 2 spins in, 2 spins out for each of these tetrahedra. The alternate squares without the crosses across are not intended to be part of tetrahedra. They represent the spaces between tetrahedra on the lattice. And if we think in terms of flux lines, then this configuration is one which has some small closed loops of fluxes. And we can go back to the ideas of degeneracy that I was talking about yesterday, and we can see that where there's a closed loop of flux like this, we can get to another ground state by reversing the orientations of all four spins on that loop. In other words, reversing the direction of the flux around the loop, and that will produce us another ground state of the system without disturbing the spins elsewhere in the lattice. So this has small closed flux loops, and there are many similar states that we obtain by reversing those flux loops. And what I want to compare it with is another state where, again, I have two spins in and two spins out. But now I fix things up so that there's just long flux lines running through the system. So now if I join the flux lines up, I have something like that. So I have large net flux and there's no other accessible nearby states. So it's got, in other words, low entropy. So then I can make an assumption for the probability distribution of this field B once I've done some coarse graining, which is analogous to the assumption we made writing down the height model. So I can guess that the probability distribution might be an exponential with, again, some stiffness. And now I just want to suppress configurations which have a high flux, and I suppress them because they've got a low entropy. And when I do the average over ground states, I should remember that within ground states, I have the constraint that div b equals 0, which, of course, as you all know, we can solve by writing the field B as the curl of a vector potential. So I could say that this is and then and you could ask at that stage what's the connection to a height model, and it turns out to be very direct. So in the height model, we had a gradient squared of the height field in our weight. So the effective Hamiltonian appearing in the exponential was a stiffness times grad h squared. But we can relate it to this form by taking A for the height model to be h times a unit vector in the z direction, and then the two-dimensional curl would simply be the gradient of the height field squared. So it's basically an extension of exactly the same ideas to a three-dimensional problem. Okay, any questions about that? Yes, that's correct. And it goes through in a rather similar way. And the point is that you should introduce one of these vector fields, B, for each component of the spin. Yeah, and it goes through and you get the right predictions. And it.
Okay. So does that mean actually the correlation function for the Spinice or maybe for the general Heisenberg pyrochlore are exactly identical?
They're extremely close, yes, yes.
Okay.
Yeah.
So at the level of the action, oh, I see. At the level of the action, these two look very similar, but okay, here the B is just linearly related to the spin, but in the 2D case, there was a more complicated relation of the height to the spin. So
yes, that's true. That's a significant difference.
Right.
Yeah, yeah. Okay, so the next thing that we should do is work out some consequences of this effective theory, and the obvious thing is to work out correlators, first of all of the magnetic fields and then of the spins. And the significant thing about this description is that we've got to a Gaussian theory, and so it's straightforward to work out correlators. I think rather than present the details on the board, I'll just tell you the answer and say a few words about why it's plausible. So to do the calculation in detail, one approach is to resolve this constraint that the divergence is zero by transforming from B to this vector potential, and then you can diagonalize this quadratic form by Fourier transform, and then you can simply carry out the Gaussian integrals. And what you find is that if you look at the correlation between one component of the spin at the origin and possibly another component of the spin at some point r, averaging overall configurations of the field, then you get something, well, it basically falls off like 1 over r cubed, and you can see that because if this stiffness is dimensionless, then just by dimensional analysis, B squared must have dimensions of 1 over r cubed. So you have something which falls off like 1 over r cubed, but it has some direction dependence. So I'll put r to the 5th on the bottom, and then you get something with the form delta ij r squared and 3 ri rj where these are components of the vector R. And so the detailed form on top, you can get either by calculation or you can check it. And one way of checking it is that, of course, in all configurations, divergence of B is supposed to be 0. So you can take the divergence of this field here, and if you take the divergence of that expression, you should be able to convince yourself that you get 0. Well, well, the fact that it's 3 is because we're in 3 dimensions, and it's, I mean, those particular terms conspire to give you 0 divergence. I think that's, I mean, it's like dipolar correlation.
Exactly.
Yeah. So the field from a dipole has 0 divergence as well. Yeah. So yeah, that's probably the easiest way of making it sound plausible. You can say that if you have a magnetic dipole, then the field away from the dipole, you know, first of all, it falls off like 1 over r cubed. And as I said, dimensional analysis shows us that this correlator should vary like 1 over r cubed. And secondly, it has divergence 0, and we know that the dipolar correlations do that. And in fact, from completeness of spherical harmonics and so on, we know it's the only possibility. Okay. I think I have time to say a little bit about how this links with the self-consistent Gaussian approximation. So I told you that a useful general approach to calculating correlation functions was to use this self-consistent Gaussian approximation. And so we had that the correlator between a pair of spins was given by elements of the inverse of a matrix, and that matrix was beta j times the adjacency matrix plus lambda times the identity matrix, where this lambda was a Lagrange multiplier to fix the length of spins. And then I explained that if we take the 0 temperature limit and go to ground states, then we end up with the spin correlator being proportional to the projection operator onto the flat band. And I explained a version of Maxwell counting, which was that the projection operator onto the flat band was made up out of eigenvectors which satisfy the rule that the sum of their components over the frustrated units was equal to 0. Okay, so what we want to do now is think a bit more about the relationship between components of this emergent gauge field and the spin variables in the original problem, which involves a challenging drawing of a tetrahedron and some axes. So that's supposed to be one of the tetrahedra from the lattice. And in the pyrochlore lattice, there are 4 sites within the unit cell. So I can number them like that. And then I want to introduce some Cartesian axes. And so I have the z-axis going like that, and the x-axis going like that. And so I want to think about a transformation between the spins at the 4 sites and the fluxes which I'm talking about in the effective description. So I have 3 components to the flux, and I have 4 variables here, so I need one more quantity, which is a quantity that's constrained to be 0 if I'm in ground states. So in ground states, 2 of the spins are in and 2 of them are out, or in Ising language, 2 are up and 2 are down. And so the net magnetization of a cluster is constrained to be 0 in ground states. But if I have excitations out of the ground state, I have some magnetization. So what I want to do is transform from the spin configurations to the magnetization, and the 3 components of magnetic field, which I introduced in this mapping to the field B. So if these are the Ising variables which are up and down, then the magnetization is simply the sum of all of them. So in this 4x4 matrix, the first row is 1. And the flux in the x direction, well, if I have the spins at the sites 1 and 2 pointing out of the tetrahedron, and the spins at sites 3 and 4 pointing into the tetrahedron, that gives me maximum flux in the x direction. So I have entries +1 and -1 like that, so that if the spins 1 and 2 are positive, meaning pointing out of the tetrahedron, they make a positive contribution to the flux in the x direction. And likewise, if the spins 3 and 4 are pointing into the tetrahedron, that's to say they're -1, they also make a positive contribution to the flux in the x direction. And in the same way, you can fill in the other entries, and they turn out to be 1, -1, 1, -1, and 1, -1, -1, 1. So the point is that you can transform from fluxes to spins and back again. So the question is what the information that we've got from the correlators of the field B tells us about correlators of the spins. And you can summarize, let me back up a bit. So as far as the correlators of the magnetic fluxes go, the interesting thing is that you have these power law correlations, and if we go to reciprocal space, which we want to do partly because if we're doing neutron diffraction measurements, then the results will be in reciprocal space. then the long distance part of the power law, which is the interesting thing, will appear at small wave vectors in reciprocal space. Yeah.
So if all the spins are pointing out, shouldn't the magnetization be 0?
Yeah, but there are two descriptions. So there's an Ising description where out is +1 and in is -1. And so in the plus-minus language, all spins pointing out is all spins +1, which is non-zero magnetization. So you have to specify which variables you're talking about, and that's the specification which I'm using here. Okay, so the point I was making was that the interesting part of the correlations in this field B are at small wave vectors. So maybe you should do a neutron diffraction measurement and look at behavior at small wave vectors. But actually you quickly realize that that can't be the answer, because if you look at small wave vectors, then you'll take a uniform superposition of contributions from these 4 spins, and you'll probe this variable m, which in fact is always very small if we go to ground states. So what we want to do instead is a measurement that looks at spin correlations and tells us about these field components B. And it turns out that to do that, you should go to points in reciprocal space away from the origin. Let me sketch the reason for that. So if we're near some reciprocal lattice point, then we can think about a Fourier component of the spins on one of the 4 sublattices, and it'll be related to the Fourier component at some small wave vector q by a phase factor which depends on the position of the site mu within the unit cell. So if we choose some reciprocal lattice point that's away from the origin, then we can get phase factors of ±1, and we can reproduce the ±1s in this matrix, and so we can probe the correlators of B. So, for example, if you look at the correlations of the Z component of B, in reciprocal space, well, I gave you the correlators in real space, and they fall off like 1 over r squared. So if you transform to reciprocal space, then you get something that goes like q to the power 0. But because these are dipolar correlations, you end up with non-analytic dependence on angle. So you end up with something that goes like q squared minus q z squared divided by q squared. Or in other words, it has a dependence on angle, which is 1 minus cos squared theta. So that was all background for going to the data which I showed. Here, so this is reciprocal space, and the origin of reciprocal space, where there's no data shown, is at the center, and up here you have one of the reciprocal lattice points that's away from the origin, and the point is that the intensity has some characteristic variation as you go around that reciprocal lattice point, and it's exactly this sort of dependence on angle around the reciprocal lattice point that reflects the dipolar correlations within the ground states. Well, okay, beyond a certain level of detail, it may be become something which is not suitable for a lecture, but I wrote down the correlators in real space, which depended on separation and also on which components of the magnetic field you're looking at. And here I've chosen a particular component, the Z component, and I've gone from real space to reciprocal space. So in real space, things fall off as 1 over r cubed, and when we do the Fourier transform, that means that we have something that has a q dependence that's q to the 0, but we also had the angular dependence of a dipolar field in real space, and that gives us an angular dependence in reciprocal space, and that's the form that we've got here, written in terms of components or written in terms of an angle in reciprocal space in that way. And so the claim is that these diffraction patterns show that sort of behavior. And it's the sharpness of the patterns that tells you that there are long-range correlations. And the theory results in that slide are from Monte Carlo simulations, but these theory results, which are the same when you match up the coordinates in k-space carefully, are from the self-consistent Gaussian approximation. Okay.
Yesterday you were showing that, say, A sub q, that plot, and you said actually in the sense because the total spin over the tetrahedras are actually 0, so that leads to kind of q0 kind of actually weight, right?
Yes.
So here, I mean, that inner whole black thing is because of that, or?
Yeah, thank you. So that's exactly correct. So the origin in reciprocal space is here, in fact. So that's h equals 0 and L equals 0. And it's black, as you say. Yeah.
And that's very sharp points actually. That corresponds to some, I mean, boundary of the Brillouin or what?
Yeah, well, this is a reciprocal lattice point which is away from the origin, and the sharpness is exactly this angular dependence which I'm talking about here.
Okay. And if I calculate some other component, like this is a GG component, like saying, do I expect actually something similar behavior, or there will be different angular dependence?
Yeah, it'll be similar, it'll just be rotated. It'll, you get the same behavior, but it'll be around different reciprocal lattice points. Okay, so the remaining time I want to use to talk about excitations, and there are several very interesting points that I want to make. So the first point is simply the analog for the Pyrochlore lattice of those pictures there. So I want to start with a ground state configuration. And, yeah, sorry, I need another row, I think. So okay, so I think that's a ground state configuration. We've got 2 spins in, 2 spins out in every tetrahedron. And what I want to do now is make an excitation in the same way as I did there by reversing one of the spins. So I'll take this spin here and replace it with one that's reversed. And now you see, of course, that we've made excitations. We've got something which is a source for this flux B in this tetrahedron, because we've got 4 spins carrying flux out and only 1 carrying flux in. And on the neighboring one, we've got 3 spins carrying flux in and only 1 carrying flux out, so we've got a sink. Just as in the 2-dimensional example, well, this is kind of a squashed 3-dimensional example, we can separate these 2 excitations because, for example, I could flip the spin here and move this excitation to its neighboring tetrahedron and carry on like that. So the picture is that one spin flip gives us 2 excitations, and these are sources or sinks of this emergent flux field that describes the ground states. So then you have a question about the statistical mechanics of these excitations. Suppose we're at very low temperatures and we just create a pair of excitations by flipping a single spin like this, and then we try and separate them. So we already argued that there's a large entropy within the ground state manifold, which is characterized by fluctuations of this flux B. And if we introduce a pair of excitations, then it's likely that those excitations will change the entropy of the ground states around them. And in particular, if the entropy were to decrease fast enough as you separated the two excitations, they could turn out to be confined. And so you want to examine how the entropy is affected by the presence of these excitations. Yeah.
Whether these charges are confined or not, isn't it just determined by the energetics? Or
well, we don't have any energetics.
Right.
Once we've made them, the
you can just
energetics are the same. But we should worry about the entropy.
Right, but since the energy is the same, I can just move them far apart, right? So
Yes,
why would they be?
But if there were very few configurations where they're far apart, then that might prevent them from separating. Okay, so that question turns out to be rather easy to answer. I mean, we've said that the effective Hamiltonian is some stiffness times the integral over b squared. And so the question is, what contribution does the presence of these two charges make to the field B? But of course, by now, we're more or less talking about electromagnetism, and you know perfectly well what the effect is of the presence of a pair of charges on the field. So if we talk in the language of electric charges, then you know the potential energy between a pair of opposite charges, and you usually think of that just in terms of Coulomb's law. But of course, if you wanted to, you could say that the energy that it takes to separate a pair of charges is precisely the energy that's stored in the electric field that you generate around the charges as you separate them. So this effective Hamiltonian depends on the field that you set up, but that field is the field that you generate because one of these charges is a source and the other is a sink. So you know that the effective Hamiltonian, or the contribution to the effective Hamiltonian, the extra contribution to HF is just given by Coulomb's law, and if you tie things up, then you'll see that K, the stiffness, plays a role a bit like the dielectric constant of free space. What you have, in fact, is a 1 over r entropic potential between these charges. So 1 over r, the energy it takes, or sorry, the entropy it takes to separate the pair of charges from an initial separation, which is one lattice constant, to infinite separation is finite. So since there's a finite potential, you have no confinement. So in other words, these classical fractionalized excitations really can escape from each other. Any questions about that? That's right, yeah.
So we would think this excitation like a monopole, anti-monopole like thing, and one can separate each other.
Yes.
Apart.
Yes.
So, okay, thank you.
I mean, if we consider actually the sort of Ising character of the sort of spin field, so this will be the kind of similar, right? The map will be exactly same. Or?
If we go to Heisenberg. Is that your question?
Yeah, I mean, my first question actually, if it is Ising, then it will be exactly same. I mean, I'm just trying to is it right?
Yeah, this is for Ising.
Ising, okay.
And if we go to Heisenberg, then this is the place where there are differences. And the reason is that as you rotate the spins in a Heisenberg model, obviously you vary the size of the different components. And here we've been using the fact that Ising spins have fixed size to give us excitations of fixed charge. And so when we go to the Heisenberg model, we lose this charge quantization. So it ends up being quite different.
In the sense, just the thing that you erased, in the sense, if I'm looking at that, say, the flux field correlations,
yeah.
I mean, that was going some 1 minus cos square theta
yeah.
kind of. So if I look at the kind of spin correlations, I mean, I'm not sure actually whether we'll get that. I mean, for
no, well, the ground state correlations go through in the same way, but the excitations out of the ground state are different according to whether it's an Ising model or a Heisenberg model. Okay, so I have time for one more point, I think, and it's a very interesting point. And what I want to do is come back to the fact that the interactions between spins are not just exchange, which you might reasonably take to be nearest neighbor. There's also a significant dipolar interaction between the spins, which is long range. Now, at first sight, that just sounds a rather inconvenient bug in this whole description. Now, the reason it's inconvenient is that the long-range dipolar interactions are certainly going to lift the macroscopic degeneracy of the ground states that we've talked about for the nearest neighbor model, simply because it's an accidental degeneracy and there must be some states with lower energy, some with higher energy. So it seems as if it's going to be an unfortunate bug, but when we look at the consequences of dipolar interactions for these monopoles, it gives us a rather beautiful feature. So I want to explain how all that comes about, and I'll do it in 2 steps. The first step will be to discuss a way of understanding why the degeneracy lifting effects of dipolar interactions on the ground states is not as severe as you might have imagined. And then the second step is to think about these excitations. So to think about dipolar interactions, it's very useful to take an intermediate step, which involves something that's known as the dumbbell model. So if we take one of these drawings of a tetrahedron with 2 spins out and 2 spins in, and we now try and think about dipolar interactions, of course we can think about a magnetic dipole as being 2 magnetic monopoles, a north pole and a south pole, with some separation. And usually you would choose that separation to be infinitesimal, so that you simply have a dipole. But in the dumbbell model, we'll think about the separation as being finite, and so we can think of having a positive charge and a negative charge, and here a negative charge and a positive charge to represent this spin, and so on for the other spins. So if we represent the spins with these dumbbells, the dipoles with finite separation between the magnetic charges, and we choose the size of the dumbbells to exactly correspond to the distance between the center of one tetrahedron and its neighbor, then you see that in these ground state configurations, the charges associated with the 4 dipoles in a given tetrahedron exactly coincide and cancel. That means that within the dumbbell model, we can think of ground states as states where we have exactly 0 charge at the center of each tetrahedron. And so these are states of a system with dipolar interactions, which are, again, exactly degenerate, like the ground states of the nearest neighbor model. So we have now, of course, it's not exactly correct to think about a dipole as a pair of charges with finite separation, but we know what the corrections to that should be. We know that a better description would of this pair of charges with finite separation would involve not just the dipole potential, but also all the higher multipoles. But those higher multipoles, well, the first non-zero one, well, they fall off like higher and higher powers of R, and so you can see that the corrections should be small. Okay, so that seems maybe like a technical detail, but it's worth talking about because it gets us a beautiful result very quickly when we think about these excitations out of the ground state manifold. So now if we flip one of these spins to make an excitation, the magnetic charges at the center of the tetrahedron will no longer cancel, and we'll get some net charge. And what you see from that is that the monopoles that I was talking about carry magnetic charge, and because of the dipolar interactions between the underlying spins, we end up with a magnetic Coulomb interaction between the charges. So they're monopoles in the sense of having a Coulomb law interaction. So there are lots of situations, obviously, where you start with a long-range interaction, which can then get screened, and effective interactions end up short-ranged. And this is, I think, the only situation I know of where we start with a less long-range interaction, a dipolar interaction, which falls off like 1 over r cubed. We wind up with an effective longer-ranged interaction, 1 over r interaction between these monopoles. So the very final point I'd like to make is to do with experimental evidence for Coulomb interaction between monopoles. And the experiment, which I'll show in a moment, involves controlling the density of monopoles with a magnetic field. So the effect of a magnetic field depends on its direction, and in this experiment you should use a field in the 1, 1, 1 direction. And if we think about a picture of a tetrahedron, then if we have a magnetic field in this direction, it will couple rather strongly to the spin at the apex of the tetrahedron, because this spin can align with the magnetic field without violating the constraint set by the uniaxial anisotropy. So this promotes well, the presence of this field promotes a monopole excitation inside the tetrahedron, and you can use this, as I say, to control the monopole density. And in particular, as you vary the field, you can go from a phase with a low density of these excitations at low field to a second phase with a high density of these excitations at high field. So that's a bit like the liquid-gas transition. And the experimental data as a function of field and temperature see a first-order transition between the low-density and high-density monopole phase and a critical point. And this transition is first order in simulations only if you take account of the Coulomb interaction between monopoles. So the nature of this phase transition gives you rather direct evidence for the long-range interactions that there are between these monopoles. Okay, so those are the points which I wanted to make in connection with Spinice, and the final lecture this afternoon will be about something different. Are there any more questions?
if one keeps cranking up this field, can one even get a crystal of these monopole, anti-monopoles?
Yes, but that's probably just an alternative description of the fully polarized state, I think. Yeah.
Is there a strong nuclear hyperfine interaction in the actual pyrochlor compounds, the holmium and the dysprosium atoms, which?
Yes, and then of course, according to the nucleus, you can have different nuclear spins, and you can even control that by using the right isotope. And so the overall answer is yes, that is a feature of these compounds, and the details I don't have in my mind.
But the magnetic field that emanates from the hyperfine coupling does not have an effect on, because that's extremely local and will be pretty similar.
I think it's an aspect of things that you have to think about at low temperatures, sort of rather below the. Rather well.
It will be somewhere. I mean, it's usually somewhere around the 0.1,
Yes.
0.2
Yes.
Kelvin
Yes.
range.
Yeah.
Okay. Any other? Yeah.
So you mentioned something about the kind of ground state correlations. I just want to know how that picture will change with temperature. Can you make some comments on that?
Yes. Okay. Thanks. So that works in a rather similar way to the way I outlined in the case of the triangular latticizing antiferromagnet. So the ground state correlations are power law, and when you go to non-zero temperature, then you have these excitations present, and they give you a finite correlation length, basically the distance between neighboring monopoles. And so because the creation of one of these monopoles costs you some exchange energy, it has a Boltzmann factor associated with it, and so the density goes to zero as you go to low temperatures, but at non-zero temperature the finite density sets the correlation length.
No, but it will still remain some power law-like or kind of exponentially?
It's exponential because of the Boltzmann factor. So it's some multiple of the exchange energy that it takes to create a monopole, and so that multiple of the exchange energy is in a Boltzmann factor.
And this another thing actually, like many of the phases of the sort of spin-ice things can be, I mean the initial part you only actually discussing only the Ising kind of interaction. So all I'm saying, where actually the effect of the dipolar term will be really important. Can you really?
Yes. Well, I mean, I said that in the first instance, the dipolar interactions seem like a bit of a bug because they lift the degeneracy of these ground states in the nearest neighbor problem. So what that tells you is that in principle, taking into account the dipolar interactions, the system should order at low temperatures. And in Monte Carlo simulations, if you use advanced techniques to make sure you reach equilibrium, then you can find the ordered state and find the ordering transition temperature, and it's I forget exactly, but it's something like 100 millikelvin. But experimentally, the system falls out of equilibrium before you get to such low temperatures.
Any other questions?
Maybe this is silly, but the spin ice thing is 3D. So can you get similar effects in 2D, but with some logarithmic confined?
Yeah, that's exactly the example of the triangular lattice.
That's the triangle.
And I ran out of time yesterday, so I didn't stress the logarithmic interaction, but as you say, Coulomb's law in 2 dimensions gives you a logarithmic confinement, entropic confinement.
So there's still a first order transition in
Oh, I see, and then can you get this? Yeah, I'm not sure. Yeah, I'm not sure about that.
If there is no other question, so let's thank John for